The learning objectives for today are we know what an open, closed, and isolated system is, and we understand the different forms of energy, in particular kinetic energy and potential energy, and that we have an idea, and don't worry, we will repeat this later, the relation of kinetic energy in molecular systems and the number of degrees of freedom. This is something that we will touch upon, but as I said, don't worry, we will repeat this later in much more detail. So to begin, let's define a system. So here we find three ideal examples of typical systems: an open system, a closed system, and an isolated system. An open system is essentially a system that we can define. A system usually is a part of a universe on which we focus our analysis. The environment, everything around it, is basically the rest of the universe, and there's a boundary in between that separates the system from the environment. And that boundary can actually be a real physical boundary, or it can be something totally imaginary, like we find here in this open system. We see that molecules can enter the system and exit the system, so there's no real physical boundary around it. And the system can also exchange heat and matter with the environment. So this is an open system. In a closed system, we actually have a physical boundary and the molecules are not allowed to leave. So there's no exchange of matter between the system and the environment. However, the system can exchange heat with the environment. In the isolated system, we have this physical barrier, but this physical barrier is now also isolating, so the molecules are still not allowed to leave, and there's also no heat exchange between the system and the environment. In the real world, that could look like this. So these are typical examples of open, closed, and isolated systems. An open system, for example, is just a test tube without a cap. So here we have, for example, air molecules that are entering our system and they can leave the system, or we have molecules in our pink liquid in here which can go to the gas phase and leave the entire system and go to the rest of the atmosphere. That would be an example for an open system. If we put a lid on it, then it becomes a closed system. So now the system is basically not able to exchange matter with your environment. So whatever is inside of our test tube stays inside of a test tube. However, the test tube is not thermally insulated, so it is able to exchange heat with the environment. If we prevent that, if we put basically some isolation around the test tube so that heat exchange with the environment is not further possible, not possible anymore, then it becomes an isolated system. Now, one more complication is that we can have closed or isolated systems which are mechanically coupled to the environment. That means if they change their volume, they basically push the environment a little bit further away, or they can shrink and the environment is pushing on them and decreases the volume of our system. So this is something that you can realize, for example, with a frictionless piston, which can move up and down and compresses or expands our system. This is what we call mechanical coupling. We will mostly focus on closed or isolated systems, with or without mechanical coupling. So these do not exchange substances or matter or molecules with the environment. However, closed systems can exchange energy in the form of heat. Isolated systems do not. Mechanical coupling, basically if we have a frictionless piston, if that is present, then the system can exchange energy in the form of work with the environment. What heat and work exactly is and how we define it, that's something that we're going to do not today, but in the following lectures. Now this is what we need to know about the systems, possible systems. Now let's discuss briefly the different types and forms of energy. So we'll see in the following that we need to consider energies themselves and exchanges of energy. Why there's a difference, we will see that later. But both are measured in units of energy. So the SI unit for energy is joule, and 1 joule is 1 Newton times meter, or 1 kilogram times meter squared divided by second squared. You will find many different forms of energy and basically small equations that give you units of energy that you will find over and over again. The first one, we already saw that, force times a distance, Newton times meter. This is 1 joule. If you remember what the definition of kinetic energy is, this is 1/2 the mass times velocity squared. You don't have to worry about the 1/2 because it doesn't have a unit, but mass times velocity squared, so kilograms times meter squared divided by second squared, that gives you a joule as well. What you'll find quite a lot as well is pressure times volume. So Pascal times meter to the power 3. If you look at the definitions of these units, Newton over meter squared times meter to the power 3 becomes Newton times meter. This is a joule as well. The gas constant times the temperature. Gas constant has units in joules per mole per Kelvin times Kelvin. This is joules per mole. So this is now an energy per mole. If we don't use a gas constant but Boltzmann constants, we get joule. So not per mole, but just joule. Temperature times an entropy. We don't know yet what an entropy is, but we will learn that. Well, the unit of entropy is actually the same one as for the gas constant. It's joules per mole per Kelvin. We define it per mole. We can also define it per molecule. But if we do it per mole, we get with the product of the temperature, we get joules per mole. And in spectroscopy, you will frequently find this product, the Planck's constant, times a frequency in hertz per second, and that will also give you an energy in the unit of joule. You might also be familiar with this product over here, which is essentially a mass times the velocity squared, just that in this case it's a velocity, it's a speed of light, which is the highest velocity you could basically have. And this is how mass can be converted into energy. So you can see, because C is very, very large, a small amount of mass, if that is converted into energy, and here we need to go beyond chemistry, you actually have to look at nuclear reactions and things like that. A small mass can be converted into a huge amount of energy. But we will not discuss that in this lecture. So let's begin looking at a couple of forms of energy, and let's begin with something simple, macroscopic, something that we are used to from the everyday world. The kinetic energy of a truck. So a 5,000 kilograms truck or a 5-ton truck at 65 miles per hour, so it's not speeding but adhering to the speed limit. The kinetic energy is expressed like this, 1/2 mv squared, which you probably have seen quite a lot. And when you plug in the numbers, well, we have a problem that 65 miles per hour is very much not an SI unit. So mile is not the unit of distance and hour is not the unit of time in the SI system, so we have to convert that first. We have 1/2 times 5,000 kilograms, which is fine, but now we have to convert the hours into seconds. 1 hour is 3,600 seconds, so 3,600 seconds per hour to convert the time unit. And then we have a mile, which is 1,609.34 meters, and this is basically then the conversion. We do that correct, and we take the velocity now in SI units to the power of 2, we square it, multiplied by the mass, divided by 2, we end up with 2.11 times 10 to the 6 joules, so 2.11 megajoules. Well, it's actually quite a lot, but you can imagine that a 5-ton truck, which is traveling on the highway, actually has a lot of kinetic energy. And of course, we are not describing that as per mole, because we cannot really imagine 1 mole of trucks. That would be something on the order of 10 to 23 trucks, which is more trucks that actually exist on this planet. That we only use for molecules. After talking about the kinetic energies, let's talk about the potential energies. You see here Newton sitting under a tree, and an apple of that tree basically gets loose and falls down on his head, and in the end rolls down to the floor. Let's assume this apple had before a height of 3 meters, and then it falls down to a height of 0 meters, and its potential energy. This is why it actually fell, because before it had high potential energy, afterwards it had low potential energy. Well, this is the mass of the apple times the gravitational acceleration times the original height of that apple. Let's assume for the actual mass of 0.1 kilograms. Kilograms is the SI unit for the mass. We could also say 100 grams, of course, but that's not what we want to calculate with. We have the gravitational acceleration, which is 9.81 meters per second squared. And then we can basically take the difference, the potential energy before, the potential energy after. This is m times gravitational acceleration times the distance and difference in height. So h1, 3 meters, h0, 0 meters. And when we plug that in, we get an energy difference, a potential energy difference before and after of 2.94 joules. Again, of course, not per moles, but just in joules. These are two relatively simple examples of kinetic and potential energies for macroscopic objects, but of course molecules also have kinetic and potential energy. So what I'm showing you here is a little simulation where we see carbon dioxide molecules. You can see the black carbons and the two red oxygens around them. This looks quite similar to the Atoms in Motion simulation software, but this is actually now a simulation that I did on my computer. So here, this is not a two-dimensional system. The molecules, you see it sometimes that they actually pass by each other. This is not because there's something wrong, but simply because there's another dimension that you don't see right now, so they can actually be below and above each other. But every once in a while, they actually collide with each other head-on, and then you can see that they start spinning and exchange kinetic energy. Well, this system has a kinetic energy as well. All the individual molecules have kinetic energy. And if you look at that as a function of time, time is here in picoseconds. 1 picosecond is 10 to minus 12 seconds. Here we see the energy in kilojoules per mole, and what we see here is actually the kinetic energy. So this is 1/2 mv squared for all these different molecules. You also will have a potential energy, and that is depending on how the molecules interact with each other. And if we look very closely, then we see that the oscillations here are essentially mirroring each other. And this is because what we're looking at here is a so-called isolated system. We now know what that is. So the number of molecules in that system is always the same. Actually, molecules that fly out here, they come in back here. This is only part of that entire system that you're looking at right now. The system is not exchanging particles with the environment. It's also not exchanging heat or work with the environment. It's completely isolated and doesn't have any mechanical coupling. And that has consequences. And one of the consequences is that the sum of the kinetic and the potential energy is always constant. Because if you're not able to exchange heat or work with the environment, so you're not exchanging any kind of energy with the environment, that means that the energy that you have in the system must always be the same. You will learn later that this is the first law of thermodynamics. And we see that reflected in these graphs. Whenever we have a spike in the kinetic energy, there is a spike in the potential energy that basically points in exactly the same direction and has the same size. Now, when we look at it a little bit more closely, we can actually define the energy of the molecules in such a system per degree of freedom. So degree of freedom is typically abbreviated as DOF. Every degree of freedom in the system has 1/2 kT energy. This is with a Boltzmann constant, so it's really per degree of freedom. If you talk about it per mole, then we replace the Boltzmann constant by the gas constant, of course. But every single degree of freedom has 1/2 kT or RT, depending on your choices, times the temperature of energy. And this is basically the direct connection between the kinetic energy and the temperature of a system. When we basically look at this graph and the kinetic energy is fluctuating, this is essentially a thermometer. This we can translate into a temperature of a system, which, as we can see, is not constant, but it's basically changing all the time. Now, what is a degree of freedom? Well, molecules can translate. Translate just means they move in the x, y, or z direction. So every molecule actually has automatically 3 translational degrees of freedom. They can move in 3 different directions. Molecules can also have rotations. This is something that is not included in the Atoms in Motion software because all the molecules are non-atomic molecules. They don't rotate. They can rotate maybe, but since they're just spheres, they are isotropic, that doesn't change anything. So this is not included here. In my case, in the simulation that you just saw, we had linear molecules, the carbon dioxide molecules. They have 2 degrees of freedom for rotations. If they rotate around the axis of the molecule, nothing changes again, so that doesn't count, but the 2 other orthogonal axes to that. You saw that the molecules were spinning in the simulation. And there are 2 different axes that they can spin around, and that gives you 2 degrees of freedom. If you have non-linear molecules, you have 3 degrees of freedom. You have 3 axes around which you can rotate, and that adds more degrees of freedom. This is actually not everything, because molecules can also vibrate, but we will learn later that vibrations are not very relevant for what we are considering in this part when we talk about thermodynamics for most gases. There are some gray areas where vibrations can become important, but that is basically material for a more advanced class. The potential energy is essentially the sum of all intermolecular interactions. We already learned what they are: electrostatic interactions, hydrogen bonds, dipole-dipole interactions, pi stacking, London dispersion interactions, and Pauli repulsions. And as far as they are relevant for basically a gas of CO2, they actually have been included in the simulation. So in particular, electrostatic interactions, while CO2 molecules don't form hydrogen bonds, they haven't been there. Dipole-dipole interactions, CO2 molecules actually do not have a dipole, so that doesn't play a role here too. They are not aromatic, there's no pi stacking, but there are London dispersion interactions and Pauli repulsions. So all this was taken into account here. And as mentioned before, the kinetic energy and potential energy, this is what we call the internal energy. In this case, this has to be constant because this is an isolated system. This is the important part. An isolated system, the internal energy is constant. This is something that we'll talk about more and more and more. Now we talked about forms of energy, in particular kinetic and potential energy, and in the following lectures we will talk about exchanges of energy, particularly in the form of heat and work, between components of a system or between the system and its environment. So this will be very, very important. This is basically at the heart of thermodynamics and will be key in the next coming lectures. But what did we learn today? As mentioned in the beginning, we learned what open, closed, and isolated systems are. We learned about the differences between different forms of energy, kinetic energy in particular, and potential energy. We looked at examples in the macroscopic world, basically the kinetic energy of a truck, potential energy, the potential energy change for an apple that falls on the tree, but we also looked at it in terms of molecules. What does it look like in a molecular system? I briefly explained how basically the kinetic energy in molecular systems is related to the number of degrees of freedom, but as I said, you should have an idea about this, but we will repeat this later. And that's it for today, and I'll see you next time.